Hey guys, welcome to our intro to static electricity video. So here's the deal. Today we're going to go through a whole bunch of the fundamental ideas in static electricity. So we're going to do a little bit of history first, just some interesting facts about how we got to where we are today. Then we're going to talk about what electricity is, kind of segue into some stuff about conductors and insulators and grounding, and just really establish the base knowledge that we need to work with electricity, because that's going to be our next unit. And I'm very excited for it. So let's hop right in here. We go back to, about the year 1730 here, which, if you think about it, really isn't that long ago for like the invention of electricity, which seems to be everywhere, right? So this guy named Charles François du Cisternay Dufay came up with something he called the two-fluid model. Look at this guy. He looks like he knows what he's talking about, right? So he says, because things can be either positively charged or negatively charged, he figured this out through some experiments. That there seems to be two kinds of things, right? There seems to be two kinds of charges floating around here. He decided that there must be two kinds of fluids that do this. There must be a positive fluid and a negative fluid. So every object has positive fluids and negative fluids in it. If an object has equal amounts of positive and negative fluid, well, then it's balanced, and he would call that neutral. It's neither positive nor negative. It's got a good balance of positive and negative fluids in it. However, fluids could flow from one object into another, just like we could pour water back and forth, right? So if I were to put two objects together and rub them together, for example, positive fluid might flow from one of them into an object. A negative fluid might leave that object and be transferred into the other one. And so your object would become positively charged. So for example, here I've got, a stick of something and a cloth. And both of these have, half and half positive and negative fluid. Now, you rub those things together, and the positive fluid from one pours into one object. Let's do it this way. And the negative fluid transfers to the other. And you get a little mix. You can see how one of them now is more positive, and one of them is more, actually, no, I should do this the other colors. One of them is more positive, and one of them is more negative. This part here. So they flow back and forth. Now, you could also do it the opposite way, right? A negative fluid could flow into an object, and then the positive fluid could leave that object, and then the object would become negatively charged. It would be the exact same drawing, basically, except flipped. Instead of, let's just draw it. We got time. Why not? We got something that's balanced. Rub something against it. That is also half positive, half negative. And so if the negative fluid is going to flow, the object we were rubbing on ends up with lots of negatives and a little bit of positives. And the rod that was doing the rubbing would end up with mostly positives and a tiny bit of negative. So this transfer, you pour fluid from just like pouring water from cup to cup. You could pour these charged fluids back and forth between objects. And so he said, all right, if two objects of opposite but equal charge come in contact to another, they will transfer their fluids. So here's a positively charged object. Here's a negatively charged object. If I bring these together, I guess together is the other way. If I bring these together, there we go, they would touch each other. So here's our two objects. And the charge would flow so that they are both balanced. So you would have two neutral objects. So if two objects of opposite charge or equal charge come in contact with one another, they transfer fluids so they become neutral. And notice they need to have equal charge, right? If I had one that was super positive and I make it touch something that is very slightly negative. Well, that's not going to actually become neutral, right? There's way too much positive in order for this to happen. And so he recognized that they have to have equal charge if they're going to neutralize. Now, it doesn't actually work that way. That was a historical model that explained some stuff we knew about electricity. But a very, very smart man named Benjamin Franklin came along next, and you might recognize him from, several inventions. But Benjamin Franklin said, I don't think there's two fluids. I think there's one fluid. And so we're going to get into his reasoning why in a second. But his model of one fluid states that there's only one type of electrical fluid in any object. So every object has an electric fluid. The amount of that fluid determines if it is neutral, positive, or negative. So it's just how much you've got. That's all. There's no positive fluids and negatives. This is just electric fluid. And depending on how much you got, that'll tell you if it's going to act positively, negatively, or neutral. So here's my object. It's got the right amount right in the middle, the right amount of electrical fluid, so it's neutral. However, if something happens to make me lose my electrical fluid, I don't have enough. I would now be negatively charged. He called that negative. If you have not enough fluid, that is now negatively charged. I said, all right, well, that fluid probably went somewhere, so another object probably has a lot of electrical fluid. We're going to call that positively charged. So if an object has a lot of, and it's not something you could see, it's not like there's sloshing around in an object, right? It was this invisible thing that acted like a fluid. But he said if you've got too much of this electric fluid, you act positively. If you have not enough, you act negatively. And the reason why he said this is because with the two-fluid model, there's no reason why positive and negative objects should be attracted to each other. And we find that they are. Positives and negatives attract. So why would that happen to the two-fluid model? So Benjamin Franklin comes along and says, well, here's the deal. Positively and negatively charged objects are attracted to one another, and this is because when these oppositely charged objects come in contact with another, the excess fluid in one is used to fill the deficit of fluid, the lack of fluid in the other. So I've got full object, I've got empty object, and they're not happy like this. They want to be neutral. And so they attract to each other because when I transfer fluid from one to the other, just like pouring water in a cup, I can get them both to equal. That's the amount that an object naturally wants to be at. That's kind of the way he phrased it. It's like their natural state. And so because of this natural state, that's why things attract to each other. So like charges repel. So if I had a positive and a positive, they don't attract to each other. In fact, they go the opposite direction. And he said, that makes sense. Look at this. Look at these two objects. They both want to lose fluid. Right? And here they are, side by side. They can't help each other become neutral. And so what happens is they scooch. They move away from each other. And on the flip side, if I had two negatively charged objects, both are lacking in fluid. Both want to gain fluid from somewhere. You try to bring them close to each other, they're not going to be able to get fluid, right? Both of them want to gain. Neither of them can gain from each other, so they repel. They move away from each other. So, because two positively charged objects, that's right here, with excess fluid cannot drain one into another, they repel. Two negatively charged objects with a deficit of fluid cannot give each other fluid. So, they repel. And now we come to my favorite model, probably because it's our current model and it makes sense to me. It's the particle model. This was invented. It wasn't invented by one guy, really. It was a bunch, well, not a bunch of work, but it was several different scientists putting little bits of a puzzle together, which is really common for science. It's not unusual for, J.J. Thomson made a discovery. And then a little bit later, Henry Becquerel came along and built on that discovery and added a little bit to it. And after that, Ernest Rutherford did another experiment, which shifted our understanding just slightly. And so these three together, all their work kind of combined, has led us to what we currently accept. our current model of electricity, we call the particle model. And I mean, we're fairly confident that this is the correct model of electricity, but I mean, if you think about it, I'm pretty sure Benjamin Franklin was pretty certain that the fluid model was correct as well. So who knows? Maybe there's another model we discover later. But so far, all the experiments we've been doing seem to work really well if we follow the particle model. So what is the particle model, right? The particle model states that objects are made up of positively charged particles and negatively charged particles. That's it. Everything is made up of particles. Some of them are positive, some of them are negative. And I mean, you guys know this already from our chemistry unit, right? You've got protons. Let's go like this. You got protons and neutrons in a nucleus, right? Positives and neutrals. And you've got electrons zipping around the outside in shells. So you've got some things that are positive, some things that are negative. As a particle molecule says that everything's made up of these positives and negatives. And it is the transfer of the negatively charged particles, called electrons, that cause an object to become either overall negative or positive. And this is important. We transfer negative charges only. We're talking about this a whole bunch of times, so you should make sure you remember this is important. We only transfer negative charges. We'll talk about why in a slide or two here, but quick refresher, the negatively charged particles are called electrons, and the positively charged ones, are called protons. Protons are positive, P+, and electrons are negative, E-. Oh yeah, first we gotta look at these guys. Handsome dudes, right? Ernest Rutherford, J.J. Thomson, Henri Becquerel. So these are the guys that were doing those experiments with electrons. Basically, they were trying to figure out what an atom looks like, to be perfectly honest. They weren't looking for electricity. They were looking for what does an atom actually look like. And so through a bunch of experiments, they kind of figured out, okay, there must be electrons in here somewhere. So it's probably just positives and negatives, just all kind of smashed around in here, right? And then we kind of went a little further and said, well, that doesn't make any sense because, well, sparks happen. How would I get the negatives out of this if it was all just mashed together? So I said, okay, maybe there's this big old positive nucleus and there's kind of like the Platter and Saturn, little negatives in a ring around the outside. Maybe that's what the atom looks like. That would work, right? The negatives can jump back and forth. Got a big old planet of positive, little negatives zipping around there. And so that was one model for a little bit. And a guy named Bohr worked with Ernest Rutherford here. They did an experiment where they took some basically gold foil and they shot a beam at it. And so that beam was, basically they said, okay, there's really only two ways this works. Either the particles in our beam are so strong that they blast right through. And that's what he expected to see. Or if our sheet is too thick, nothing's going to come through at all. And then we just got to make a thinner sheet. So they took this sheet and they actually made it of gold, which is interesting because it's something you can spread really thin. They shot these particles at it. And what they found was they had a medium amount go straight through, which they expected. But then they kept getting little hits. And they extended their detector and they found little hits all around the edges. And they said, okay, pump the brakes here. If our model of an atom is a huge, heavy, positive thing with a little ring of negatives, then this foil should be made of basically a solid wall of positive charge. Why do we have things deflecting? Like, yeah, we got a lot of charges coming through here. But like, imagine putting a piece of tissue paper up and then shooting a gun at it. How many times would you expect the bullet to hit the tissue paper and deflect sideways? Or worse, hit the tissue paper and reflect back at you? I mean, if you're me, if I'm shooting a gun at a piece of tissue paper, I expect that to happen 0% of the time. That should never happen. That bullet should go straight through, right? So they took a look at this model and they said, this doesn't work. That's where our model of the atom came from. A tiny little positive nucleus with electrons all around the outside in this big cloud. He says this makes sense because the vast majority of the time, when you shoot your beam, it misses the nucleus. It goes right through the cloud and hits over here. Life is good. I'll do this in red so it shows a little better. It goes right through the cloud. Life is good. But every now and again, you bullseye that nucleus. And so as your beam comes, it hits the nucleus, and that nucleus is so dense and heavy that it deflects the particle. It was like putting a couple like steel balls behind your tinfoil. Every now and again, you're going to clip one of these steel balls, and that would deflect the bullet. And so that's where the actual Bohr model, which is also kind of invented by Rutherford, the Bohr-Rutherford model it's sometimes called, came from. It was that very famous gold foil experiment. It's been a while since I did my history on Becquerel, but I believe he helped to figure out masses and charges of the electrons. So when an object gains electrons, because again, electrons are in the outside. They're the only ones that can move. When an object gains electrons, it has more electrons. So, okay, here's my thing. Normally, let's just say it's got 2 of each. Now, in reality, every object has billions and billions and billions of charges. There would never be like 2 charges. You wouldn't even notice 2 charges. They're way too small. But just to make this easy to see, I'm not going to draw 2 billion charges because you guys don't want to be here all day, and neither do I. So when an object gains electrons, so I'm going to rub something together here, and some of those electrons rub off onto the object. So my object ends up, it still has the positive charges, but now it's got, so the positive charges haven't gone anywhere, they're just swamped with negatives. When an object gains electrons, it ends up with more electrons than protons, and remember electrons are negative, protons are our positives. That's what we call negatively charged. So if an object gains electrons, it's going to be negatively charged. Now, same object. So these are like electrons transferring on. Same object. But now instead, what if the object were to lose electrons? We take these electrons off. We transfer them back to the other rod there. What I'd be left with is an object that has more protons than electrons. It might still have an electron somewhere, but it's got more protons than electrons. So overall, we call that positively charged. So it all has to do with electrons. The positive charges don't move. Only the electrons do. If you put electrons on something, you make it negative. You steal electrons off of something, you make it positive. When an object has an equal number of protons and electrons, so I got 4 positives there, 4 negatives there. That's what we would consider neutral. Oh, I can write that neater. There we go. All right. Now, oppositely charged objects are attracted to one another, and when they come in contact with each other, they're not pouring fluid back and forth. They're transferring electrons from the negative object to the positive object. So I got 2 positives and 4 negatives on that object. So this one is negatively charged. One, two, three, 4 positives and 2 negatives. That one would be positively charged. And so they're attracted to each other. And if they touch, if they come in contact with each other, because our charges are usually transferred through contact, what would happen is the negatives would flow in whatever direction it takes to neutralize these objects. So you'd end up with, that one's neutral. This would have 2 extras at the top. So you'd end up with a balanced here, neutral. 1, 2, 3, 4 negatives, 1, 2, 3, 4 positives, and neutral there. So if oppositely charged objects come close to each other, they get attracted, and when they touch, when they come in contact, electrons are transferred from one to another. Now, they don't necessarily have to touch directly. If they're just close, and one has a lot of negatives, and the other has almost no negatives, so it's just mostly positive charge, sometimes, well, like charges repel, right? And look at how many like charges are on here. Look how many electrons there are there. And they're very close. They're literally pushing each other so hard that they can sometimes jump. And when a bunch of electrons jump all at once, hold on, I did that one backwards. There we go. That's a spark. That's what we see as a spark. So when it said electrons jumping from one object to another, which is, I mean, it's almost contact. They have to usually come pretty close to get a spark. It's rare to get sparks longer than, like, you know, a centimeter. We can make them, and we're going to do that in this unit at some point, but it's pretty rare to see them outside of lightning bolts, which are wild amounts of energy. And so on the flip side, like charges repel each other. Hold on. Over here. Yeah, objects are transferred. Okay, good. So, thing to remember. Positive and positive repel. Negative and negative repel. Positive and negative attract. Opposites attract, like charges repel. You've probably heard opposites attract. It's the same in physics here, same in electricity. Opposites attract. Now, be sure to note, again, super important here. We've said it before. We're going to say it again. I've said it a ton today. Be sure to note, it is the electrons that transfer, not the protons, right? Protons are stuck in the middle of the atom. They're stuck in the nucleus. They can't go anywhere. They're big, they're heavy, they're held tightly in the very core of the atom. They're not moving. It's only the electrons. So I got protons, neutrons, protons. Like, they're held very tightly there in this nucleus. But my electrons are way out here. And they're zipping all over the place. So they're very easy to take away. You can get to those, you can zip them around, you can transfer them, you can move them, you can make them jump. So remember, it's the electrons that are transferred. Electrons, not the protons. And so this brings us to ideas of conductors and insulators. Substances are given different names, or sometimes we call them types, different types of substances, based on what they do with electrons. And so the first category we're going to look at here are insulators. So we call a substance an insulator if it holds on to its electrons really tightly. So the electrons can't move. If I put electrons onto an insulator, they stay still. They can't go there. So here's my insulator. If I put a couple negative charges on this end over here, they're going to stay there. They won't spread out through the object. They're stuck. They don't move very well, which means the object holds a negative charge. It's really difficult to charge up something that's not an insulator, because if I try to charge it up, the charges can flow through the entire object and out into and sometimes they just jump out into the air, sometimes they go to the ground, but anything that's touching that object can soak up those extra charges. And so if electrons are placed on an insulator, they stay still and you can charge it up really well. So you'll find that most of the stuff we do in static electricity, which we'll talk about static in just a second here, is with insulators, because they're going to hold our charges for us. If electrons are removed from an insulator, so I take electrons off on this side, so I'm not adding positives, I'm taking away negatives. So the leftover protons are still there. So that side ends up positive, but electrons nearby can't move to fill the gap. Our object's going to hold that positive charge. These electrons can't jump over there and cancel it out. You'd actually end up with a negative side and a positive side if you had an object like this, because they can't flow to actually neutralize each other. Either way, we call that electricity static, which is a word that means not moving, not changing. So when we talk about static electricity, we talk about electricity that's building up on an object and is stuck there. It's static. It doesn't like to move. That doesn't mean it can't move, right? Sparks are a jump of electricity. Obviously, it needs to move. If we're going to charge an object, we have to be able to move those electrons somewhere. But once they've gone there, they don't like to move. They're stuck in place. So that's static electricity. Electricity that doesn't move much. We're going to look at electricity that does move. We call that current electricity. Current, not like today, but current, like a river. It flows. So static doesn't move. Current electricity, which we'll look at later, does move. And so most of our insulators, some examples would be stuff like plastics and rubbers. If you look at a wire, it's usually coated in a rubber coating, right? That rubber's an insulator, and it means the electricity inside the conductor can't get out. It's trapped by the insulator, and so it stays in the wire, which is good. It means when you touch the wire, it doesn't jump onto you and give you a shock. So plastics, rubbers, PVC, all kinds of materials are insulators. On the flip side, we've got conductors. Now, these are materials that hold their electrons very loosely. Electrons can move around. So here's a nucleus, here's a nucleus, here's a nucleus, here's a nucleus. I've got, an electron, and it can jump back and forth between different atoms that are close by. Those electrons are held pretty loosely. They can fly all over the place. So if I take my conductor and I try the same thing I did last time, I charge one end negatively, I try to get the other end charged up positively, it's just not going to work. What's going to happen is those negatives will spread out and they will make sure that it's all equally balanced. The negatives are attracted to positives. That's why they spread out, right? So these negatives would move this way because they're allowed to. Electrons are allowed to jump. So they would move over to where all the positives are and end up neutralizing it. And not only that, but there's a lot of negatives on this side here. And so they repel each other. They'd be pushing each other to jump to the other side. And so they're going to end up neutral pretty much no matter what. Now, this makes it really difficult for a conductor to hold a charge. I mean, you could say, all right, smarty pants, Mr. Burns, what if I only put negative charges on this conductor? Now nothing can flow anywhere. This could have a negative charge, right? And you're right. You could charge a metal up with a negative charge if you wanted, as long as you don't touch it ever. Because if I touch it with my finger, this is going to be a very terrible finger. There we go. There's my finger. Fingernail. My knuckle. My hand. Poke. Hey, that wasn't so bad. So if I poke this, give me some knuckles. You know what? Let's just say I'm going to touch it with a wire, and I'm going to attach it to the Earth. Here's planet Earth down there. Same idea. If you poke it with your finger, you're also usually touching planet Earth through your feet. It's a conductor. These negatives are trying to repel each other, and so they repel each other right down your finger, or down the wire in our case, out of the object. And how long are they going to repel for? Well, they're going to keep repelling until the object is back to neutral. What if it repelled more? What if extra negatives charged out? Well, then this would end up positive, and electrons would go the other way through your finger or through the wire and get sucked back up because positives and negatives attract. So it always ends up going to neutral really quickly. So conductors are very difficult to keep charged because the charges can flow through them and can jump to anything nearby to try and get rid of the extra charge. So conductors can hold a charge, but it's difficult because the electrons can travel to the ground. Way easier. Now, if you want to find a conductor, most metals, almost all of them, are good conductors. That's why wires are often made of copper, right? Copper conductors, copper wires, because copper is a metal and it's going to conduct really easily. So let's talk about that. Grounding. So they travel to the ground. We literally call it grounding. Grounding a charged object makes it neutral. Doesn't matter what your charge is to start with. Doesn't matter if you're positive. Doesn't matter if you're negative. If you ground an object, it's going to become neutral. So how do we ground it? Well, it doesn't have to be the earth. You don't have to connect it to the literal ground. It's a good option, but basically all you need is a large neutral object, a very large neutral object. So they will either remove electrons if the object's negative, or they'll give you electrons if the object is positive. Now, the reason it has to be very large is because if it is very large, it doesn't notice the loss or gain of electrons, right? Earth, if you look at the size of the Earth, I don't know if you know this, a little bit of knowledge, but the Earth is really big. If I were to take off, 4 billion electrons from the Earth, Earth doesn't even notice. It's like, you hop on the scale and then I drop a grain of salt in your pocket. It's not going to add to your mass at all. You're not going to see a noticeable difference. If I soak up a few thousand or a few million or a few billion charges from Earth, it's not even going to notice. And so you need a big neutral object, but you can connect anything charged to a big neutral object. And if your objects are small, which everything is compared to Earth, it'll soak up or give as many electrons as you need. So very often we do use Earth. You see this most spectacularly with lightning, right? We have lightning, obviously, in storms and things, and lightning hits objects on Earth, and that lightning is made of electrons. Or not made of electrons necessarily, but it is a static charge. It's either too much negative or too much positive in the clouds. And those charges have to get balanced somehow. And so we see this when stuff is struck by lightning. If you have a big tower, a lot of them have what's called a lightning rod on the roof. So they have, here's my tower. It's fantastic. There we go. We'll put some wires on there to hold it up. Why not? There we go. Big tower, one of the blinking lights on top. Life is good. A lot of times these towers will have an extra little thing on top that has a wire, a big thick wire, that runs all the way down the side of the tower or building or whatever it is into a spike underground and a big old copper plate at the bottom. And so the plan is lightning comes and it hits the top of the tower. Lightning always hits the easiest object to reach, which is the top. And so instead of going down the tower and frying all your electronics and lighting your building on fire, because the spike is metal and the wire is metal, that's an easy path to take. So the lightning takes the metal path all the way down into the ground and then can dissipate into the earth. You have grounded that charge without shocking your tower. There's a video on YouTube, actually, Google it if you want. It's the Empire State Building in a lightning storm, and it gets hit like 3 times in a single storm, hit by lightning 3 times. It's like, yeah, whatever. It's got this lightning rod. That's what it's designed for. Now, your house is going to be grounded as well. Your house is much less likely to be hit by lightning, but if an appliance malfunctions and builds up electricity, or if something's rubbing together, like you have a motor, something like motorized, like a drill or a saw that you're running, and it generates some electricity, or a wire, maybe it just breaks and or gets worn out or frayed, and the electricity starts to take a shortcut, a pathway through something that it shouldn't. We call that a short circuit. That could cause fires very easily. And so we ground houses in such a way that there is any extra electricity can get out of the house and into the ground. Now, most houses, older houses, are grounded through the plumbing system. A lot of houses have copper pipes, so they just hook up everything to the plumbing. Electricity, you have extra electricity somewhere, extra electrons are not enough, it's building up. Electrons can flow through your copper pipes, and where does the water come from? And where does it go? Well, it comes from a water supply pipe, which is metal and which is underground. It's basically a big one of these spikes that exists in the bottom of your house, except it goes sideways instead of underground, but it comes out of your basement usually. So the electricity will run through your house's copper pipes, down to the cold water intake, and out into the ground where it can dissipate for free. New houses don't use copper pipes. They use something called PEX, which is a kind of plastic, which is an insulator. And so they're a little trickier. Every circuit that they have has to be connected back to your main circuit panel with a special grounding wire. And so they have extra grounding wires installed that go to your circuit panel somewhere. And then your circuit panel is connected to the cold water intake pipe because those pipes are still metal. And so wherever the water comes into your house, they use that as your ground. Everything else might, if you have a newer house, will go through the electrical system. They actually put a grounding wire in. If you have an older house, it might just be grounded through your plumbing, which is interesting. So, quick thing to note. Here is my object that does not have enough negative charges on it. Same object, but now it has too many negatives on it. There we go. So they both have 5 positives. One's got too many negatives, one I took all the negatives off. So this object starts out positive, this object starts out negative. What does it look like when we ground it? So here's Earth. Unlimited electrons. It can take or give as many as it wants because it is huge. So if I were to connect this object to this object with a wire, what's going to happen? You got to be careful here because a lot of people say, oh, the positives travel to Earth and then it's gone. No, do not move positive charges. If I want to neutralize this, electrons are attracted. Negatives are attracted to positives. So electrons go from Earth through my wire to the object. And so it will become 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. It'll become neutral. Again, it'll stop. Electrons will stop flowing once it reaches here because there is no repelling, it's neutral, and no attracting. The positives can't attract the negatives because they're already paired up. They're already canceled out. There's nothing left over. There's no repelling because you don't have extra negatives or extra positives. So once it hits neutral, there's nothing else to happen. So a positive object sucks negative charges up. Let's change my color here. What if I have something negative and I hook it up with a wire? That's the exact same thing, but in reverse. Electrons get repelled out of our object and into the Earth. So if something is negative, electrons go to the Earth. If something is positive, electrons come from the Earth. And eventually, you would end up 1, 2, 3, 4, 5. 2, 3, 4, 5. Balanced. That wire would still be there. But again, if it's neutral, there is no repelling and there is no attracting. So that's how grounding works. It doesn't matter if your object's positive or negative. The attractive and repulsive forces of positives and negatives will force electrons to move wherever they need to move, to Earth or from Earth, depending on your object, in order to balance that out. And it will continue to move until it reaches neutral, because that gets rid of your repelling and attracting charges. Or forces, sorry. So that pretty much sums up our intro to static electricity. I know it was a long one, guys. Great job hanging in there with me. But this is all the information you should need to be able to kind of take off and understand and learn about static electricity. So thank you very much for your time, guys, and I will talk to you later.